The double-slit experiment. This simple experiment has baffled physicists for over a century. It challenges our very understanding of reality. Imagine shining a light through two narrow slits. We expect to see two bright bands on the screen behind, right? But the universe has a surprise in store for us. Instead, we see a pattern of multiple light and dark bands, an interference pattern. This suggests that light, which we perceive as particles, also behaves like waves. How can something be both a particle and a wave? This is the heart of the mystery. This experiment isn't just about light. It holds true for electrons and even larger particles. This wave-particle duality is a fundamental principle of quantum mechanics. Quantum mechanics describes the strange and counterintuitive behavior of matter at the atomic and subatomic levels. It's a powerful theory, but it's also deeply mysterious. It raises more questions than it answers. What does it really mean for a particle to be in multiple states at once? How does the act of observation seemingly collapse these possibilities into a single outcome? Quantum mechanics tells us that the world is inherently probabilistic. This means we can only predict the probability of an event, not the event itself. For example, we can calculate the probability of finding an electron in a particular region of space. But we can't say for sure where it is until we actually look. This is a radical departure from classical physics, where everything is deterministic and predictable. The double-slit experiment highlights this probabilistic nature. Each particle doesn't travel through one slit or the other. Instead, it exists in a superposition of states, going through both slits simultaneously. This creates the interference pattern we observe. The act of observation, of trying to determine which slit the particle went through, collapses this superposition. The particle then behaves like a single particle, passing through one slit or the other. The interference pattern disappears. What if there's another way to understand these strange quantum phenomena? What if the universe is not just probabilistic, but also computational? This is the central question we explore in this essay. We propose a new way of thinking about the double-slit experiment. Imagine the universe as a giant computer. This computer is constantly calculating probabilities. It's updating these probabilities at discrete intervals, like frames in a movie. This idea might seem outlandish at first, but it offers a compelling explanation for the observed wave-like behavior of particles. In this framework, the interference pattern isn't created by particles physically interfering with each other. Instead, it emerges from the underlying computational process. The universe is essentially calculating the probability of finding a particle at each point on the screen, taking into account the geometry of the slits. Think of it like this. The universe creates a probability wave that spreads out through space. This wave isn't made of any physical substance. It's a mathematical construct that represents the likelihood of finding a particle at a particular location. The wave interacts with itself, creating interference patterns just like waves in water. When we make an observation, we're essentially taking a snapshot of this probability wave. This computational perspective doesn't contradict quantum mechanics. Instead, it provides a deeper level of understanding. It gives us a glimpse into the machinery behind the probabilistic curtain of the quantum world. It suggests that the universe isn't just random. It's following a set of rules, a cosmic code, to compute probabilities and determine the outcomes of events. This computational view of the universe is more than just a philosophical idea. It leads to testable predictions. If the universe operates on discrete time steps, we might be able to detect this. For example, we could look for tiny fluctuations in the interference pattern of the double-slit experiment. These fluctuations would correspond to the universe updating its calculations. Another prediction is that there might be limits to the accuracy of our measurements. This is because the universe can only compute probabilities up to a certain level of precision. Finding these limits would provide strong evidence for the computational nature of reality. It's important to note that this computational perspective doesn't diminish the mystery of quantum mechanics. The universe is still deeply weird and counterintuitive, even if it is a giant computer. Questions about the nature of consciousness and the role of the observer remain. But this framework offers a new way to think about these questions. It suggests that consciousness might be fundamentally intertwined with the computational fabric of reality. The act of observation might not be just about collapsing wave functions, it could be about accessing and influencing the underlying computations that govern the universe. This computational perspective opens up exciting new avenues for research. It encourages us to look for evidence of the universe's computational processes in a variety of physical phenomena. Imagine the universe as a vast canvas. This canvas is constantly being painted and repainted with probabilities. These probabilities determine the likelihood of every event, from the formation of galaxies to the interactions of subatomic particles. The double-slit experiment in this view is just a tiny glimpse into this grand cosmic painting. It shows us that the universe isn't afraid to embrace chance and randomness. But it also suggests that there's an underlying order, a computational framework guiding this cosmic dance of probabilities. The idea of the universe as a computer is not entirely new. It has been explored by physicists, computer scientists, and philosophers for decades. But recent advances in quantum computing and our understanding of the universe's fundamental laws have breathed new life into this idea. We are now beginning to develop the tools and theoretical frameworks to investigate the universe's computational nature in a more rigorous and scientific way. The future of physics might lie in unifying quantum mechanics with computer science. This could lead to a more complete and elegant description of reality, a description that embraces both the strangeness of the quantum world and the precision of the digital realm. So, is the universe a giant computer? The answer is, we don't know, yet. But the evidence is mounting that there's more to reality than meets the eye. The universe is not just a collection of matter and energy, it's also a realm of information, computation, and perhaps even consciousness. By exploring these ideas, we are not just unraveling the secrets of the cosmos. We are also pushing the boundaries of human knowledge and imagination. We are embarking on a journey that could ultimately lead us to a deeper understanding of our place in the universe and the nature of reality itself.